Welcome my friends, welcome to my next lecture. Now in my last lecture I have discussed the proof of Taylor's theorem. That means if I have a analytic functions on some domain, so suppose domain is ball of center 0 and radius r, or ball of center z0 radius r, then we have seen that I can express my functions or I can have the expression of f around the point z0 in terms of power series, and of course that power series is unique. So proof I have discussed. So for today's lecture I will see a couple of applications of this theorem. In other words, concrete examples I will talk about. Like for example, if I take the exponential functions, then you will see it will have a what is called power series expansions because it is analytic functions everywhere in the complex plane. So if I take some point in the complex plane, I can have the power series expansions around that point. And once I have that one, now since I have discussed the concept called what is called power series, Taylor series. Now if you remember in my earlier discussions I talked about, or when I defined the definitions of exponential functions in terms of Euler's formula, there I have said that when I will talk about power series expansion, then I will give the justifications that why the Euler's formula is I can have the e to the power I theta, it's exactly equal to cosine theta plus I sine theta, because e to the power I theta, you may think about that. Now since I have a power series, so I have the expressions of e to the power z. Now once I have expression of e to the power z in terms of power series, then I will have the expression of cosine of z and sine of z. Then I will see the formula that you assumed earlier, that e to the power I theta is cosine theta plus I sine theta. Now I will prove it. Once I have the expansion, or once I have the notion of power series or Taylor series, since exponential functions, sine function and cosine functions are analytic functions on the entire complex planes, or it is an entire function. So therefore if I talk about the power series, I can talk, because Taylor's theorem ensures us, if I have a function which is analytic in a nice domain, and if I take a point inside that domain, then I will have a what is called power series expansions around that point, and that series is known as Taylor series. So my plan for today's lecture is to give or calculate some concrete example, verify what is called Euler's formula, and then at the end I will compare a little bit of real the Taylor's theorem that you are comfortable with and the complex one. So that's the plan. Okay, so just to recall it, so like in the Taylor's theorem, this is, you look at the statement of the Taylor theorem once again. So this is my Taylor's theorem. So if I have analytic functions on this domain, then fz has a power series expansions. That means I can write my f as a power series, that means around the point z0, n z minus z0 to the power n, where z runs over my domain B at z0. So therefore, and you can conclude that the radius of convergence is greater or equal to r. So this is the power series, right? So now the point is that this is around the point z0. Now if I take a nice function which is analytic everywhere, so if I talk about power series around the point 0, so then you will have a nice expansion. Okay, so that's what the remark is said. Okay, yeah. Okay, so before that I have already calculated, like for example if I want to calculate like f of z is equal to e to the power z, it is an entire functions, right? It is analytic everywhere in the complex plane. So therefore if I want to talk about the power series around the point I, you can easily do that, because Taylor's theorem says that I can have the power series expansion. Not only that, the coefficients in the power series can be written in terms of the derivatives of the sum functions or given functions f. So therefore the given functions f is given, so therefore I can write my coefficients of the power series. Now if I know the coefficients of the power series, then I know the full power series. So that's how. So if I calculate coefficients, I already talked about, this is e to the power I divided by n factorial. So therefore this is the corresponding power series around the point what is called z0 is equal to y, and if I calculate the what is called radius of convergence, it is point at infinity. Radius of convergence is infinity because my functions, exponential function f is analytic everywhere in the complex plane. So this is one of the little note or remark. So if f is an entire functions, so therefore I can have the power series expansions around the point 0. So therefore I can write my functions f in terms of power series or Taylor series, that is called the Taylor series, n from 0 to infinity, n z to the power n, where n is nothing but fn0 divided by factorial n. Then I say that, okay, now come to the exponential functions. Now one hand I have a power series, one hand I have exponential functions. Now I say that these two things become same. So that is why I started with a power series 1 by factorial n z to the power n. The radius of convergence of this power series is point at infinity. So therefore the functions, if I write this, the sum function is f of z, which is analytic everywhere in the complex plane, that means it is an entire function. This is the first conclusion. Second conclusion is that again in the before Taylor's theorem I have proved a theorem. What is the theorem? If I start with a power series, then I say that the corresponding sum function is analytic. Not only that, if I take the kth derivative of the nth term, and if the corresponding new power series is sum function is g let it be g, then g and the sum functions f will have a relation. That means the kth derivative of f is exactly equal to g. In other words, if I take that say first time differentiation of my nth term, or say kth time differentiation of my nth term, and if I get the new power series, then the new power series can be written, or the sum of the new power series or some function of the new power series is nothing but the kth derivative of the original sum functions of the given power series. So if that is the case, or sometimes I can say that term by term differentiation is possible first time, second times and nth time. Okay, so this is the case. Now this is the sum function. So therefore if I do the term by term differentiations, because of this what is called power series, if I take the derivative, I can conclude that it is exactly equal to f. So this is the second observation. Third observation is that now when I define exponential functions in terms of what is called Euler's formula, there we also have the property that e to the power z, if I take the derivative, that is also e to the power z. Now I have a functions f, which is nothing but the sum functions of the corresponding power series. I have another function e to the power z, whose derivative also the e to the power z itself. Now the question is there any relations? Answer is yes, there is a relations. So to do that, what I have done, I am considering a new functions h of z, which is fz divided by e to the power z. F is entire, e to the power z is entire, quotients of two entire function, it is entire functions, so h is an entire functions. Now if I take the derivative h prime, and you can conclude that h prime is equal to 0, because f prime is equal to f and e to the power z derivative is e to the z. So therefore what I have proved is that h prime is vanishes, or the derivative of h vanishes on the entire complex plane. Complex plane is nice domain, so is a simply connected domain, or everything is very nice domain. So therefore I can say that since my function is entire functions or analytic functions, its derivative 0, so therefore h is constant. So therefore you can conclude that f of z is equal to c times e to the power z, and from that equations you can conclude that c is equal to 1, because you can take put z is equal to 0, this is f of 0 c times e to the 0, which will imply c is equal to f of 0, and I know what is my sum function f, so from there it follows that c is equal to 1. So therefore it turns out that your functions f of z is equal to e to the power z. So therefore now since I have a power series expansion, so now I can say that my power series e to the what is called this 1 by factorial n z to the power n, what is the sum function f, and that f is nothing but e to the power z. So now I think it is quite clear. So now if I say that what is my exponential functions, I will say that yes, e to the power z will have, or I am saying that e to the power z is nothing but sum from n from 0 to infinity 1 by factorial n z to the power n. So that's it. Okay. Now you see, so now we will define the exponential functions in terms of power series, because I know the concept of power series, I know the what is called properties of power series, I know Taylor's theorem. So therefore I can define e to the power z, which is the sum functions of the given power series, that means z to the power n divided by factorial n. Now in the next time you will see Euler's formula. Earlier I have defined e to the power theta or e to the power iz in a different way by assuming something. Now I have the exponential, right, in terms of power series. The next part is that when I have defined sine function and cosine functions in terms of exponential functions, so therefore it is expected I can write my sine and cosine function in terms of power series. Answer is yes. So the sine and cosine functions can also be written in terms of power series. And what is the formula? If you recall the formula, your sine of z, which is e to the power iz minus e to the power minus iz divided by 2i, and you know the expression, or you have the power series expansion of e to the power z. So this is the expression you know. So you just replace z by iz and do some algebra. If I do this algebra, so you evaluate it, so therefore put the value e to the iz, this is this one, put e to the minus iz, exactly this is this one, then you just combine it. So this is exactly what is called the power series expansion of my sine function sine z. Similarly, you can do the cosine functions, because this is the formula. That's how I have defined what is called my cosine of z. Now you know series expansions of e to the power iz. You know series expansions of e to the power minus iz. You just add it. So this is the corresponding power series expansions of what is called my function cosine of z. So now I have the power series expansion of e to the power z, sine z and cosine z. Once I have that one, you see, now I can prove what is called Euler's formula that I have assumed when I talked about that e to the power I theta. What is that? Cosine theta plus I sine theta. If you remember that, I have defined like this one. Defined. So because theta is real, so therefore I say that, okay, consider this complex number cosine theta plus I sine of theta. If I consider this complex number, it turns out that this is exact. At that time I denoted at e to the power I theta. Now I have the power series expansions of e to the power z. That means I know the expression of e to the power I theta, and I know the series expansion of sine and series expansion of cosine. Now the question is, can I say that this is exact equality is there? Answer is yes. Look, so e to the power I theta, this is the power series I just said, because e to the I theta is a complex number z. So this is nothing but sum over n from 0 to infinity I theta to the power n divided by factorial n. Now you just break up into two parts. One is the even part and one is the odd part. So this is the even part, so that means 1 by 2n factorial I theta to the power 2n, and this is the odd part, 1 by 2n plus 1 factorial I theta to the power 2n plus 1, and therefore how I can write it. So therefore now since it is even, so therefore I square will come out, so therefore I square is minus 1, and here you will have I square to the power n, but you will have theta to the power 2n plus 1. But since I am dealing with odd power 2n plus 1, so therefore one I factor will come outside. So therefore this is exactly equal to n from 0 to infinity, what is called I square is minus 1 to the power n theta to the power 2n divided by 2n factorial, and this is plus I times theta to the power 2n plus 1 minus 1 to the power n divided by 2n plus 1 factorial. Now look, go back. What is the expansion of sine? Sine z is, this is the corresponding expansion, right? I just explained. So now in place of z is equal to I theta, if I put what is sine theta, sine of I theta, or say theta, if I just put it theta, right? So let me just look at it, okay? Yes, so this should be theta, correct. So now if I put sine theta, so what is that? So this is sine theta, which is n from 0 to infinity minus 1 to the power n theta to the power 2n plus 1 divided by 2n plus 1 factorial. In fact, that series expansion you also familiar with in the real case as well. So now look at, so this minus I square is minus 1, so I square is minus 1 to the power n, so therefore this portion n from 0 to infinity theta to the power 2n minus 1 to the power n divided by 2n factorial, okay. So what is that? This is n from 0 to infinity minus 1 to the power n theta to the power 2n divided by 2n factorial, right? Now go back to the expansion of this. Look, so if I put z is equal to theta, so the cosine of theta is equal to n from 0 to infinity minus 1 to the power n theta to the power 2n divided by 2n factorial, theta to the power 2n divided. So that means what is that? This is cosine of theta. So therefore this object will give you what is called, this is the object will give you cosine of theta. And what about this one? This is give you the sine theta, but what is that? This is sum from n from 0 to infinity minus 1 to the power n theta to the power 2n plus 1 divided by 2n plus 1 factorial, right? And look at here. Sine, if I put theta, this is minus 1 to the power n theta to the power 2n plus 1 divided by 2n plus 1 factorial. So therefore this object, this is the object will give you cosine theta, this is the object will give you sine theta. So therefore you will have the formula e to the power I theta is exactly equal to cosine theta plus I sine theta, right? So therefore earlier I have assumed it to define e to the I theta like that. Now I have the notions of power series and I know the series expansions of e to the power z, and it implies what will be the corresponding series expansion of sine and cosine. Once I have the series expansion, that one, then I can easily verify the Euler's formula. Okay. So therefore, whether you will write it or whether you will assume it, or so that means you can by default, then there should not be any confusions. So if I write e to the power I theta, you can easily write, you don't have to define it, you can just write this is exactly equal to cosine theta plus I sine theta, because you know the expansions of cosine, you know the expansions of sine in terms of power series, on the other hand you have the expansions of power series expansions of e to the power I theta, and all are becomes equal. So therefore now you can say that yes, if I say that what is my e to the power I theta, you can just say that this is nothing but cosine theta plus I sin theta. It will be a complex number, and what is that complex number? It is cosine theta plus I sin theta. So I think that now there should not be any confusion. So therefore you can use blindly e to the I theta is equal to cosine theta plus I sin theta, because now everything is well understood since I have the notions of power series. Okay, so now another nice what is called conclusion or like applications of this power series or like Cauchy's estimate. You see what is this? So now I am starting a polynomial. So what is P? P is a polynomial of degree n. Okay, because what is the coefficients of the highest power? 1. 1 is non-zero. So therefore P, I am starting with a polynomial P of degree n. So that means it is a naught plus a1z up to a n minus 1 z to the power n minus 1 times z to the power. It's a polynomial of degree n. N is greater or equal to 1, assume. So then one can easily check that there exists a constant m such that this should be true for mod z greater than 1. You can easily check it. Why? This is straightforward example kind of exercise. So why? Because you see if I estimate p of z, what is that? This is modulus of z to the n plus a n minus 1 z to the n minus 1 up to say a 1 z plus a naught, right? This is the one. Then you just use the triangle inequality. So if I use the triangle inequality, this should be mod z to the power n plus mod n minus 1 mod z to the power n minus 1 up to mod a1 mod z and plus mod a naught, right? But you see mod z is greater than 1. Now if mod z is greater than 1, then if I hit by mod z to the power n minus 1 both sides, then what will happen? This is greater than mod z to the power n minus 1. That means this will implies mod z to the power n minus 1, which is strictly less than mod z to the power n, because I am just multiplying mod z to the power n minus 1 both sides of this inequality. So therefore I can have the inequality that modulus of z to the power n minus 1, which is strictly less than mod zn. Similarly you can have mod z is greater than 1, right? So therefore you hit it by mod z to the power n minus 2 both sides. So this is mod z to the power n minus 2. So what it will imply is mod z to the power n minus 2, which is less than mod z to the power n minus 1, and mod z to the power n minus 1, which is also less than mod z to the power n. So in other words, what I am trying to say is that you see you will have modulus of pz is dominated by this one. Now that I can make dominated by mod z to the power n, keep as it is. Now the second one a n minus 1 times mod z to the power n minus 1, but I just proved that mod z to the power n minus 1, which is strictly less than mod z to the power n, so therefore this is mod z to the power n. Plus next term, what will happen next term? So next term will be mod a n minus 2 times mod z to the power n minus 2, but mod z to the power n minus 2 also dominated by mod z to the power n, so therefore you can write a n minus 2 mod z to the power n minus 2 next term. If I go like that, then you can prove that mod z, which is also less than mod z to the power n, okay, successively if I do the process. So therefore this is also mod a1 times mod z to the power n, and of course 1 is less than mod z and hence mod z to the power n. So therefore this is mod a naught mod z to the power n. In other words, what I am trying to say is that you can have the estimate of modulus of p of z, which is dominated by, take mod z common from each term, so therefore mod z to the power n, then what will remain will have 1 plus a n minus 1 mod plus a n minus 2 mod up to a1 plus a naught. Now you just write this is the constant, because I'll have finitely many a0, a1 up to an minus 1 and 1. So if I write this is as capital M, so therefore you have the estimate modulus of pz dominated by m times mod z to the power n, and this is true for all mod z greater than 1. So first one is trivial. So therefore if I have a polynomial of degree n and n is greater or equal to 1, then you can always have the estimate. That means I can estimate my modulus of pz, which is dominated by m times mod z to the power n. That is perfectly all right. So now the next question. What question is that? I am asking the converse. That means what kind of functions polynomial? Polynomials are analytic functions. In fact, analytic in the whole complex plane. So therefore it is an entire function. So therefore I can say that polynomial is an entire functions having the property this kind of things, right? Now I am asking the converse of this question. That means if I start with an entire function, suppose you will have this kind of what is called assumption. That means absolute of f of z, which is dominated by some constant times mod z to the power n, and this is true for mod z greater than 1. Okay, so you will have a constant m which is independent of z such that this is true. Now the question is, can I say that f is a polynomial of degree at most n? So this is the question I can ask. The question is clear. I hope it is clear. So what I'm doing is that I'm starting with a polynomial of degree n is greater or equal to 1. Then I conclude, or I convince you that if I estimate that polynomial, I can have the constant m which is independent of z, such that modulus of pz is, I can dominate modulus of pz lesser or equal to some constant m times mod z to the power n, and that is true for mod z greater than 1. So that I just explain it. So now I am asking the converse of it. Since polynomials are entire functions, so now I am starting with this question. If I start with an entire function f having this kind of properties, that means there exists a constant m such that modulus of f of z which is dominated by m times mod z to the power n for mod z greater than 1. Can I say that f is a polynomial of degree n? Answer is yes, you can do that. And that is why complex analysis, that power series or Cauchy's theorem will come into the picture. Now look, since f is an entire function, so I will have the Cauchy's estimate. So what is Cauchy's estimate? If you remember, if I have a nice domain and if I have a contour of center some point z0 on some radius r, then the kth derivative of f at the point 0, because since I am talking about entire functions, so I am keeping my point z0 is equal to 0. So I will have the estimate of the derivative of kth derivative of f at the point z0 in terms of the factorial n, then there is a constant m. M is the supremum of absolute of fz, where z running over my circle, and then you have the what is called radius, you have the corresponding radius of the contour, that r to the power n. So this kind of estimate you might know. So if I use that estimate for these functions f, then the kth derivative of f at 0 can be estimated. So if you remember, kth derivative of, or maybe I think if you remember, nth derivative at the point z0 will be estimated by factorial n times m divided by r to the power n. Okay, these things if you remember. So what is factorial n? Factorial n coming from this is n, perfectly all right. R is the radius of the contour, so that means R is the radius, the contour I am taking, that means it is circle of center z0 radius r, so therefore this R factor is there. But what is m? M, if you remember, m is the supremum or maximum of absolute of f of z, where z runs over, I think, that CR at the point z0, or maybe CR. CR is, what is CR? CR is the contour z minus z0 is exactly equal to R. So this is, you know. Now you see, so therefore if I replace z0 by 0, so therefore I will have the estimate. So I will have, of course, this k factorial will be there, r to the power k will be there. And then what I will have, I need to have the estimate of the absolute of f on the contour. But on the contour, it is a contour of radius r. Now you see, on the contour, what kind of estimate you will have? I need the estimate supremum. But you see, this is the assumption it is given, right? Now if this is given, that this is, since modulus of fz is dominated by, say, m times what is called mod z to the power n, so therefore if I take r is large, so therefore I crosses that one. So therefore if I take a contour, say, of say r, and r is way greater than 1, then in this contour also my function satisfies this kind of inequality. So there, what will be the supremum of this fz on that contour? Certainly it is dominated by m times r to the power n, right? Because absolute of f of z which is dominated by m times mod z to the power n, what is the value of the mod z here? This is r. So therefore r to the power n. So therefore this is actually dominated by factorial k, m times r to the power n divided by r to the power k. I hope this is clear. So because here z0 is equal to, this is the origin I am talking, the point z0 is equal to 0. So therefore what I need is that I need r is sufficiently large so that it crosses the value 1. So therefore in the contour I need the maximum of the absolute f of z on the contour. Now on the contour you already have the estimate which is dominated by some constant time mod z to the power n. But on the contour, what is the value of mod z? Is r. So therefore the supremum that I need on the contour, which is dominated by m times r to the power n. So therefore by Cauchy's estimate, this absolute is dominated by this one, which is exactly equal to factorial k m divided by r to the power k minus n. Now look, numerator is constant, k is fixed, m is fixed. Now look at the denominator, it is k minus n. Now you see, if k is strictly greater than n, and if I take r approaches to infinity, because r, capital R is in my hand, I can take as large as I can. So if I put r approaches to infinity, since k minus n is positive, that means this is goes to 0. That means I can say that f of k0 is 0 for all k greater than n, right? That's the kind of conclusions. So that is why by Cauchy's estimate I will have this one which goes to 0 as r approaches to infinity for each k greater than 1. Since f is an entire function, so therefore, okay, so first this is the conclusion I am done. Now f is an entire function. Now since f is an entire function, it will have a power series expansion around the point 0. That means you will have this kind of expansion. F of z is equal to a sum over k from 0 to infinity akz to the power k. And what is my ak? If you remember in the power series, ak is nothing but kth derivative at the point 0 divided by factorial k. That is the expression you know in terms of in Taylor's theorem you know. So not only you will have the expressions of an entire functions around the point 0, but I can write the coefficients in terms of the sum function. So this is the one. But you see, just now I have concluded if f has this kind of estimate, fk's are 0. So fk is 0 for all k greater than n. So therefore, even though it is an infinite series, so only finite infinitum will survive, because fk 0 means what? Ak is 0. So therefore, it will implies, so you can say that ak, so that means this will implies ak is equal to 0 for all k greater than n because of this fact. So therefore, I will have a power series fz which starting from, so I will have a power series fz starting from k from 0 to infinity akz to the power k, but because of this estimate hypothesis of the functions, I conclude that this is 0. So therefore, this will implies a or fz is looks like k from 0, so k greater than n, so k from 0 to n akz to the k. But what is this? This is actually polynomial of degree at most n. So that is why I am saying. Since f is an entire function, so I know the what is called series expansion of f in terms of power series around the point 0. So by observation, ak is 0 for all k greater than n because of this estimate. So therefore, f is a polynomial of degree at most n. So this is very nice. So therefore, if I have a polynomial, it will have a growth estimate, right? So modulus of p of z is dominated by m times mod z to the power n for mod z greater than 1. Conversely, if I have a nice function like entire functions, and if I have the growth estimate like modulus of f of z dominated by m times mod z to the power n for mod z greater than 1, then f is a polynomial of degree at most n, and that is a very nice applications of what is called Cauchy's estimate. So this is a very nice exercise or applications of Cauchy's estimate or power series, you can say. Okay, so couple of remarks I should say. So remark is that, so now I have discussed Taylor series around the point z naught, z is equal to z naught. Now it says that the Taylor series of my functions f around the point z naught is equal to 0 is called the what is called Maclaurin series. This is another name. Now another this observation you already familiar with. If fz is analytic in this domain, all those z where mod of z minus z naught is less than r, then by Taylor's theorem fz can be approximated with arbitrarily high precision of bipolynomial p and z of highest degree. So that's what it is now. So because if in that domain, since my function is analytic, I have a power series expansions. So that means I have the expansions of f of z like a n z minus z naught to the power n, right, n from 0 to infinity. Now what is the convergence of this? So this convergence means you just have to take the what is called partial sum n from 0 to infinity n z minus z naught to the power n. Now what is n from 0 to capital N, okay. Now what is Sn? Sn, since I am truncating this power series, so it is a polynomial, it is a polynomial of degree say at most n. And what is the convergence of this power series? So Sn converges to f, say absolutely on the domain of convergence uniformly if I take a smaller closed unit disk there. So therefore what I am trying to say is that if I have a power series or Taylor series, so therefore I can what is called approximate my functions f in terms of polynomial of higher degree. That's what it is, because I am approximating my f in terms of Sn, and Sn is nothing but a polynomial of degree capital N. So that's what I have written. Fz can be approximated with arbitrary high precision by a polynomial p and z of sufficiently high degree, because if capital N approaches to infinity, degree of my S capital N increases, so that is why. Third one is that this is another important observation, is that alternative way to find radius of convergence of Taylor series. Now if I have a Taylor series, then there is a formula in terms of limb soup or in terms of what is called ratio of the coefficients. But another way you can visualize it is it says that suppose you have a domain, okay, maybe domain is not like very nice domain like open unit disk of center z naught radius r. Suppose you have some arbitrary domain D, and suppose your function is analytic at the point z naught, then the radius of convergence r of the Taylor series. Now if I have a domain, arbitrary domain D, and if I take a, and suppose my function is analytic there, and if I take a point z0 inside D, then around the point z0 I will have a Taylor series of my function shape. Okay, so around the point z0, or I can write my f in terms of the power series of z minus z0, right, or power series around the point z0. So what it says is that, so if my function is analytic at the point z0 and z0 sitting inside arbitrary domain, then the radius of convergence R of the Taylor series about the point z is equal to z0, that I will have by Taylor's theorem, is the distance from z0 to the nearest singularity at which my functions fails to be analytic. So what I am trying to say is that, suppose this is my domain D, suppose this is my point z0, okay. So my function is analytic, suppose here, or suppose if you don't care about the analyticity, suppose at a point z0 it is analytic. So since at a point z0 is analytic, so therefore in a neighborhood or small neighborhood of z0 we will have the power series expansions of my functions. That means I can write f in terms of the power series around the point z is equal to z0. Now the question is, what is the radius of convergence? Because since I am talking about power series, so it is expected it will have a radius of convergence. You can guess the radius of convergence. It says that you check the nearby point around the point z0 where you maximum have the analyticity. That means you should find what is the nearest point, say z prime, where my functions loses analyticity. And if suppose my point here is the z prime where my functions loses analyticity, that means there is a singularity. That means if I take the distance z0 to z prime, this is the distance. So this distance, if I say that this is say r, so r is the distance from z0 to z prime or z star, which is the nearest singularity from the point z0. This r should be the radius of convergence of your power series. That means if I take a ball of center, say z0, and radius, say this r, this is the corresponding what is called domain of convergence of my power series that I know, or I know the expression of, I know the equality of f in terms of power series around the point z0. So that's what it says. So alternative way to find, so if fz is analytic at the point z0, then the radius of convergence are, so first of all analyticity, by Taylor's theorem it says that it will have a power series expansions. Now once you have a power series expansion around the point z is equal to z0, it will have a radius of convergence. What will be the radius of convergence? You just try to find out the nearest singularity from the point z0, right? The r is the distance from z0 to that singularity. You can expect that this r is the what is called radius of convergence of your power series of your functions f around the point z is equal to z0. So that's what. Then the radius of convergence r of the Taylor series of f around the point z is equal to z0 is the distance from z0 to the nearest singularity to z0 at which fz fails to be analytic. That means my functions is lose the analyticity. That means the point z star that I am saying, it is the what is called singular point. That is, you consider the distance or absolute between z0 and z star, where z star is the nearest singularity to the z0. That is the corresponding radius of convergence of your power series of your functions f around the point z is equal to z0. This is the couple of observations. Maybe this observation you will see later on, I will use it, this kind of observation. Instead of calculating via lim sup and ratio of what is called coefficients, that is another way to like guess what will be your radius of convergence of your power series around the point z is equal to z0. If your function is analytic at the point z is equal to z0. So this is the famous mathematician Maclaurin. So this Scottish mathematician who has kind of invented these things, this object. Okay. So this is one of the nice this called I should say comparisons between real functions and complex functions. Now you see that is why you will see that analyticity is very strong property. Now you see what is real Taylor's theorem and real you know. So let me just discuss, then it will be clear. Now I already discussed Taylor's theorem. Now by Taylor's theorem, if a function f is analytic on D, that means if it is infinitely differentiable on an open set. So by Taylor's theorem, if a function f which is infinitely differentiable in an open set, then fz can be expanded in terms of power series in D. So that's how just now we have observed. So if I have a function f, if I have a domain D, if my function is analytic in my domain, that means it is infinitely differentiable, then I can expand my function in terms of power series in D. Okay. Now the question is that kind of conclusion. Another conclusion is that this result is no more true in case of real valued functions with real variable. So that is not true. Why is that? Because you see, Okay, so this result is not true in case of real valued functions of a real variable. For example, if I consider these functions. Now, what is these functions? These functions f of x is a very nice function. Okay, e to the power minus x square if x is non-zero, 0 if x is equal to 0. Now, this function, it's a map from R to R. And what kind of function it is? You just check. This function is very nice function. Very nice function means in real analysis I am talking about differentiable functions. Now, you see, except 0, of course it is exponential functions, it is differentiable functions. The important part is that these functions also differentiable at the point 0. Not only it is one times differentiable, but also it is infinitely many times differentiable at the point 0. Not only that, derivative of kth derivative of f at the point 0 is exactly equal to 0. You check it. This is for all k, 1, 2, so on and so forth. So this is very nice. So these functions f of x is equal to e to the power minus x square, x is non-zero, f of 0 is equal to 0 is infinitely many times differentiable in a neighborhood of x naught is equal to 0. So if I remove the point 0, then of course it is infinitely many times differentiable because it is actually exponential functions. So only the problematic point is x naught is equal to 0. And the functions, the way I have the functions, you see these functions actually one can check it is also infinitely many times differentiable at the point 0. And not only that, what is the value of the derivative, kth derivative of these functions? So kth derivative of these functions at the point 0 is exactly equal to 0. So this is very nice. So then I am saying that fx cannot be represented by a power series around the point x naught is equal to 0. Why? Suppose you see, if I write this power series around the point what is called x naught is equal to 0, then what will be your expression? Fx should be n from 0 or k, so k from 0 to infinity, say ak, and then you have x to the power k around the point 0, and what will be an ak? Ak should be a relations with the sum functions, that means k derivative of f at 0 divided by factorial k. Suppose I am writing my functions f in terms of power series around the point 0, that means I will have this kind of expression, f of x is equal to this expression, where ak is this one in a neighborhood of in a neighborhood of the point x naught is equal to 0. But you see, since if I write my functions in terms of power series in a neighborhood of x naught is equal to 0, I will have this expression where ak is this and in a neighborhood of x naught is equal to 0. But what I observed is that derivative, kth derivative of my functions f, which is 0 for each k. If these things happen, that means ak is 0. That means ak is 0 for all k. Now, since ak is 0, so therefore right hand side is a 0 function. So therefore, one hand I have the equality f of x is equal to sum over k from 0 to infinity akx to the power k in a neighborhood of 0, but by properties of function it says that kth derivative of f at 0 is 0 for all k. So therefore I am saying that f of x is equal to 0 functions in a neighborhood of the point x naught is equal to 0, but which is not the case, because if I take out the x is equal to 0, my function is non-zero functions. So I am demanding that, so if I assume that I can write my functions in terms of power series around the point x naught is equal to 0, then I am saying that f of x should be exactly equal to k from 0 to infinity akx to the power k, where ak is fk0 divided by factorial k. But I already claimed that, or you can check that ak is equal to 0 for all k, because kth derivative of f at 0 is 0 for all k. So therefore it will, so this is this equality in a neighborhood of 0, the point 0. So therefore you will have f of x is equal to 0 if I assume that f has a power series expansions in a neighborhood of 0. If I assume that one, that would implies that f of x is equal to 0 in a neighborhood of the point x naught is equal to 0. So that means existence of power series around the point x naught is equal to 0 implies f of x is equal to 0 in a neighborhood of x naught is equal to 0, but which is not the case, because the way I have defined the functions, if I just take out the point x naught is equal to 0, so if I take a point x naught which is non-zero, my function is non-zero functions. So the right hand side I am saying it is 0, left hand side it is non-zero, so contradictions. Why contradictions? Why the contradictions arise? Because I started with the wrong assumption. I assumed that fx has a power series representation around the point x naught is equal to 0, which is not the case. So therefore fx cannot be represented by a power series around the point x naught is equal to 0, even though my function is nice. That means it is infinitely many times differentiable at a point 0. So that is the clear distinctions between what is called real analysis and complex analysis. In complex analysis, if I have functions which is analytic or infinitely many times differentiable, then if I take a point at z0 inside my domain, then I'll have a power series around the point z0, z is equal to z0. But however, in real analysis, which is not the case. That means I have a function say which is very nice, but still I cannot write my functions around that point in terms of power series. So that's what it is. Fx cannot be represented as a power series around the point x0 is equal to 0. So therefore, the property of analyticity or complex differentiability is very rigid compared to the real differentiability. This is another clear distinction between the complex analysis and real analysis. This is one. So our real Taylor series, so now since you are kind of done real analysis bit, so our real Taylor series of a real valued functions of a real variable, if you know, so that means if you know the Taylor theorem, so you will see you have a Taylor theorem and there is a remainder term, right, for the real valued functions. If I deal with real valued functions of real variable, the Taylor theorem says that it will have a one Taylor theorem around the point, then you have a Taylor remainder. Now if Taylor remainder goes to 0, then it will have a Taylor series. So that's what I have written. So our real Taylor series of a real valued functions of a real variable converges if and only if the Taylor remainder goes to 0. So that is the kind of notions you are familiar with in the real analysis. So if I have a nice functions or real valued functions of real variable, so Taylor series nothing but you go to the Taylor theorem, look at the remainder term. If remainder term goes to 0, then I can say that it will have a Taylor series expansions. But in complex case Taylor series, the remainder term is irrelevant. Well, the Taylor series will converge in the largest disk that one can fit inside the domain of analyticity. So that means if I have a function analytic in a domain D, if I take a point z0 inside my domain, and in that domain around the point z0, I will have a what is called Taylor series. Forget about there is no remainder term or nothing. You will have an expansion of Taylor series and it will converges what is called absolutely in the largest domain that I can fit inside my domain of analyticity. So that means if I have a ball of center z0 radius r, there I will have the expansions of actually Taylor series. Forget about the remainder term. That is, the remainder term is irrelevant. I will exactly have the expansion, infinite series expansions, and the convergence is absolutely on the domain of convergence there. Well, and if I come to the little bit kind of smaller subset, it will be converges uniformly. So that's what it says. So a Taylor series of a real valued functions of a real variable converges if and only if Taylor remainder goes to 0. But in complex case, there is no concept of Taylor remainder. As long as my function is analytic at a point z0, I will have a Taylor what is called Taylor series, which converges absolutely in the domain of convergence or in the larger domain. I can fit into the domain of analyticity of my functions f. So this is like comparison between real functions and complex functions. Okay, so maybe I think I should stop here. So this is 2 exercises I have given. So like for example, if I give this kind of problem, for example, if I have this function f of z e to the z divided by 1 minus z, what will be the power series around the point z0 is equal to 0, and similarly what will be the power series of this around the point z0 is equal to 0. Now you can easily guess. So because you see what kind of function it is. So this is e to the power z divided by 1 minus z. Now it will have a singularity at the point z is equal to 1, because this is analytic, because once the function's value crosses 1, then in the denominator it will have a singularity. So that means you can easily guess it will have a power series expansions around the point z0 is equal to 0, and the radius of convergence of these parts is maximum 1 or 1, because if it crosses 1, it will contain the point 1, and there you will have the what is called singularity. So that's just now I have discussed the nearest singularity from the point z0, that means nearest singularity from the point z0 is equal to 0 is 1. So therefore the radius of convergence of these parts is 1. Similarly here also. But to get this kind of power series, you can easily guess it, because you see if I know the power series of 1 by 1 minus z, then what is this function? This is nothing but the, if I let it be g, then g prime is nothing but f. So therefore if I know the power series of f, then I know the what is called term by term differentiation, so then you can have the power series of f. So therefore if I take the derivative of g, which is nothing but the f, so term by term differentiation, so if I know the power series of 1 by 1 minus z, I will have the power series of 1 by 1 minus z square. So therefore you don't, or well, there are many ways you can do that. Right, that it is, since I need the power series, so it will have the form say an z to the power n, n from 0 to infinity, and what is your n? It is nth derivative at the point 0 divided by factorial n. So you know f, then you calculate the nth derivative and evaluate it the kind of coefficients. That's another way you can do that. Or also you can do that the known series expansion, suppose you know, and then apply your earlier theorem that term by term differentiation is possible, so then you can have the formula. Here you can also do the same thing. So you can say that this is of the form n z to the power n from 0 to infinity, where n is equal to nth derivative of f at the point 0 divided by factorial n. So either you can calculate all the coefficients and get your what is called power series, or what you can do, you will have two known functions. One is e to the power z, that power series you know. Another is 1 by 1 minus z, that's also power series you know, because I know the geometric series expansions. So then you have to what? You have to take the product or Cauchy product. So if I know the Cauchy product, then I can have the what is called series expansions of my functions f around the point z naught is equal to 0. This is another way. Okay, so two ways, but I think if I calculate the coefficients for each n, it might be difficult for you. So instead you should apply this kind of Cauchy product formula. That means you have known series expansions, take the Cauchy product, you will have the expansions. Here I think it is better, get the known series expansions and use the what is called term by term differentiation. That is also okay, and also I think this is also fine. You just take the derivative, because derivative you can guess it, what will be the nth derivative of these functions, then you can evaluate it and you can have the formula. Maybe in my next lecture I will start explaining that one, and then I move to what is called Lorentz series. Okay, I think I should stop here. Then I will move to my what is called next week lectures. In next week I should start with once again giving some solution of exercise 1 and exercise 2, and then I move to the concept of what is called Lorentz series. Okay, so that means if I have an analyticity, then I have a power series expansions around the point of analyticity. Suppose if I have a singular point, can I have the some kind of series expansions around that singular point, and that turns out to be what is called Lorentz theorem or Lorentz series. Maybe that concept I will talk about in my next week. So I think I should stop here. Thank you.